Since you know that in classical mechanics the conservation of momentum is a very important principle, and we define momentum as the amount of motion, and it is mathematically defined as mass times velocity. So in this video I am going to show that this definition of momentum is not general, so we need another definition. So now this is our example. So look here, we have two objects of mass m. Both these objects, object 1 and object 2, have same masses, that is m, and the object 1 is moving along the positive x direction and the object 2 is moving along the negative direction with the same speed v. So this is before collision, and when the collision happens, so we assume that this collision is perfectly elastic such that no kinetic energy is lost. So the object 1 moves in the vertical y direction and the object 2 moves in the negative y direction. So now let us look at the conservation of momentum. So if pxi is the total linear momentum along the x direction before collision, so this is 0 because the objects have same masses and they are moving with equal and opposite velocities, so therefore it is 0, and the total linear momentum in y direction is also 0. After the collision, the particles are moving along the y direction and there is no motion along x-axis. So the initial momentum, so the final momentum along the x direction is 0, and the final momentum along the y direction is m times v plus m times minus v. So this is also 0. So now you see that the momentum conservation is satisfied here. But now we assume that there is a frame S prime and this frame is moving with speed minus v along the negative x direction. So in this frame, this particle 2 will appear at rest. So now this is our situation that the particle 2 is at rest and particle 1 is coming towards this particle 2. So you know, we in previous video we derived the velocity transformation equation, so we can use that equations to get our velocity. So this equation is ux prime is equal to ux minus v divided by 1 minus v by c squared ux. So ux the speed in the x direction in the unprimed frame and v is the frame velocity. So now you look here, before the collision the velocity of this particle 1 is v, so therefore ux is equal to v, so I can put v in the place of ux in this expression. Also the frame velocity in this particular case is in the negative x direction, so therefore we have minus v as frame velocity, so this gives me v plus v divided by 1 plus v by c squared into v. So this gives me 2 times v, 1 divided by 1 plus v squared by c squared. So this is the velocity in the x direction, and since the particle 2 appears to be at rest, so it does not have any velocity. So the total momentum along x direction will be, you know, our definition mass times velocity, so I can multiply this velocity with mass. So this gives me 2 times mv divided by 1 plus v squared by c squared. So now this is the total momentum along x direction before collision, and of course there is no motion along y direction, so therefore the momentum along y direction will be 0. And now look at the case of after collision. So when the collision happens, so this particle m2 which is at rest in S prime frame will also move. So therefore it will have both the x component of velocity and y component of velocity. So now we can find the x component. So the ux component will be, I am using the same transformation equation, but if you look here, so after the collision there is no velocity along x direction in the S frame, so therefore ux is 0. So if I put ux 0, and also since the v is minus v in this case, the frame is moving in the negative x direction, so this gives me plus v. So we can find the velocity in x direction, which is v. And also for the particle 2, since you can see from figure that the both of these velocities are parallel to each other, or you can use the velocity transformation equation. So it is also give you v. So the total momentum along the x direction after the collision will be mass time velocity plus mass time velocity, which is equal to 2 times mv. So now compare these two equations. So total linear momentum along x direction before collision is 2 mv divided by 1 minus v squared by c squared, and total linear momentum along x direction after collision is 2 times mv. So these two are not equal, so it means that the momentum is not conserved in the x direction. So now you see, that is our problem. Also you can find the, for y component you can find use the transformation equation. So this is our transformation equation. Uy prime is equal to uy divided by gamma 1 minus v by c squared into ux. So now you see, before collision there is no motion along y-axis, so therefore the momentum will be 0, and after collision, yes, there is a motion. So we can find, so you can check these two cases. So here in this figure, so uy is equal to v. The y component of velocity is v in s frame, so therefore I can put here v, and this is equal to, because ux is 0, so it gives me v by gamma. And therefore the other particle m2 is moving in opposite direction, so these components will be opposite. So you can do this. So this gives you 0. So the momentum in the y direction is conserved in the s prime frame, but in the x frame it is not conserved. So that is our problem, because the momentum conservation fail. So it means either the definition of momentum is not correct, the way we define the momentum is not general, or this conservation of momentum principle is not general. But since we know that the conservation of momentum is a very important principle in mechanics, so therefore we trust that this momentum conservation is true, and now we need to modify the definition of momentum. The way we define the momentum, we need to modify this definition. Since the momentum conservation is failing because of there is a relative motion, so I can multiply a factor f of v. So now this is our new definition. So momentum is equal to mass time velocity, which is our old definition, but now we are multiplying another factor, which is f of v, and we choose this f of v such that when this velocity becomes 0, so this factor goes to 1, means that at low velocity regime, so we will get our old definition, because this is a very good definition. Okay, so when we perform certain calculations, so we can find the value of this f of v. So this f of v is basically 1 over 1 minus v squared by c square root. So if I put the value of f of v, so this gives me m naught v divided by square root 1 minus v squared by c squared. So now this is our definition of momentum, the relativistic momentum. This is known as relativistic momentum, and it is a more general definition. But you know that the old definition, we are familiar with our old definition, so we want to keep the old definition. So therefore this factor m naught by square root 1 minus v squared by c squared can be given a name m, so that we can get our old definition. So p is equal to mv. So this is the same form as m naught v, where this m is defined by this relation, and this is known as relativistic mass. So this relativistic mass m is not a characteristic properties of the physical system. So it is just a mathematically constructed quantity, and it is constructed to keep the old form of the momentum definition. Okay, so you should not worry about this, that what is this m. So this m is just a mathematically constructed quantity, and it is not a characteristic property of any physical system, because let's say if someone asks you what is the relativistic mass of electron, so this is in fact an invalid question, because this is not a physical quantity. and this is how we can keep our old form of momentum. Also, we can define another parameter. So I can define this v over 1 minus v squared by c squared, and I can call this as proper velocity. So now you see here p is equal to m naught into proper velocity, which is eta. So now this is also giving us our old form. So these two conventions are used to keep the old form of the definition of the linear momentum. So that is how we define the relativistic momentum. So that is all for this video.